Okay, in the next talk I would like to show some of the comparisons between some of the different measurements excuse me, that we've been making. This work is, we've just started on this really. A lot of the projects we've been setting up, some of the equipment and the instruments, and at this stage we're starting to get good results now, and we're able to start making some meaningful comparisons between the results. Okay, so first thing I'd like to do is just have a quick review of some of the requirements, some of the things that are of interest to measure, and I'll just go over a little bit of the work, some work that we did at MPL previously over a more limited temperature range, because I think it just helped illustrate some of the things that we want to measure and some of the things we want to get out of the comparison. And I'll say a little bit about electric field effects and temperature measurement, and then we'll go over some of the results that we've got so far. Okay, so first of all, I said earlier about, for example, an actuator for opening and closing a valve. Then for these actuator applications, we're looking at large fields generally, and we're also interested in thermal expansion. So these large fields, the effective D33, or the strain that you can achieve at a particular value electric field, may or may not bear any resemblance to a small field D33 measured, for instance, using resonance. And so one of the questions that we have to ask if we're working on this kind of application is how relevant is published data that might be based on, for instance, resonance measurements. How good an indication is that of the piezoelectric performance that I'm going to get? And some of the other things, these are just some sketches really, some ideas. We mentioned earlier about the effects of the Curie temperature on the piezoelectric performance. So this top graph here shows, for instance, this line here is the strain, the S min is the strain at zero electric field. And you can see the thermal expansion in that, and we can see clearly the change in strain, change in remnant strain at the Curie temperature. If we apply finite electric fields or large electric fields, then you go straight through that point and you don't even see it. It's more or less continuous. You wouldn't know that there was a transition there. And so the influence of the Curie temperature on the performance of an actuator is something that you may not see from small field measurements. So I think we have to be, and this is one of the things that we'd like to understand more about, is that correlation between the small field and the large field measurements and the influence of electric field on piezoelectric performance at high temperatures. And just out of interest, really, so we can see a little bit of this happening in this. This is a PZT type material with a very low Curie temperature of around 160 degrees, and you can see in these strain loops, this is a whole set of bipolar strain loops, and you can see a drift in position which corresponds to the thermal expansion. These are 3-1 strain, and you can see we've got the classic butterfly loop, typical butterfly loop, and then when we get to around the Curie temperature, the hysteresis disappears and we have this electrostrictive behaviour. But if you were to look at the top of the loop, then you wouldn't see any discontinuity going through the Curie temperature. And in fact, even well above the Curie temperature, we're still getting a reasonable level of actuation. Okay, and some of the work that we did on this low temperature, the nice thing about a low Curie temperature material is that we can investigate these properties through the transition above the Curie temperature without all of the complexities of electrode materials and so on. And we can see with this that even the piezoelectric behaviour can still be described as an electrostriction. One way of looking at piezoelectric behaviour is that it's electrostriction offset by the remnant polarisation. And we were able to show that that really works quite well for parts of the loops over a wide range of temperatures. So this little moving here, you can see this part of the curve is fitted to a parabola, which would be descriptive of electrostriction. This is the ferroelectric regime, and then above the Curie temperature it collapses all onto a parabola. So we can use that to describe a lot of the thermal expansion and piezoelectric expansion in these materials. It also tells us something about charge control. So our charge control is a method often used for linearizing and removing the hysteresis in a control system using a piezoelectric device. And you can see that, I'm sorry, but the axis has disappeared, but this is charge along the x-axis, that's strain, and you can see that as we go up and down the loop, there is no hysteresis and it's very linear. It's actually not quite linear. It again follows this electrostrictive parabola. Okay, so some of those considerations I think are things that we would like to explore only at higher temperatures and with higher temperature materials as well. Okay, so on to some of the results. We've mentioned about temperature measurement, and this has been a common issue with I think with all of the systems that we've been working with, is that simply putting a thermocouple in the vicinity of the sample doesn't give us a good temperature measurement, and so for both the exact system and for the MPL system, we've used some dummy samples and applied a correction based on those, which gets us to a reasonably tolerable measurement of the sample temperature. When we're operating in vacuum, then things can get even more difficult. In air, the air helps to maintain temperature equilibrium, and when you take that air away, then there's nothing to move the heat around to maintain the equilibrium between different parts of the test environment and the sample. And so this is some work that PTV have been doing on their interferometer to look at the stabilisation time for the temperature. If you've got very small contacts between the heat source and the sample, and it's surrounded by vacuum, then it can take a long time for the heat to go into the sample, and you can have quite a long thermal time constant. And so I think, Guido, you've been evaluating the thermal time constant for these temperature steps, so that they can make sure that the sample temperature corresponds with the measured temperature at the time of the test. There's some important things there is around thermal contact, and one of the things that we want to try and achieve is to get good thermal contact between the sample and whatever it is that's controlling the temperature, so the source of the heat. Okay, and these are some results from PTV on the temperature stability in the vacuum. So I think it's fair to say now you've solved this problem and you're getting very good thermal stability in these samples with a reasonable level of confidence as to how closely the measured temperature matches the temperature of the sample. Okay, another issue which we've touched upon several times during presentations is the effects of leakage current, and we're doing some measurements of leakage current to try and put some figures on that, because it's important for a whole range of the measurements that we're doing. And so you can see here, this is a PZT disc and with measuring the resistance as a function of temperature. This is 1 over temperature on this scale, and this is a log scale on the resistance. So we can see that that once we get above, that would be 1,000. Once we get above a few hundred degrees Celsius, then the resistance drops linearly on this log scale. So the conductivity increases very rapidly as we heat these materials up. There's quite a lot of work in the literature that's been done on conduction mechanisms and the contributions from things like vacancy mediated processes or even direct band gap conduction. Here are some of the results comparing some of the piezoelectric measurements now, and we've seen some of these results in the previous presentations, but I've tried to summarise some of these on a single graph, and we can see for the large field D33 measurements in this particular sample, which is one of the Leeds samples, then we can see a very, very large D33 at high field measurement. And if we measure this small fields using the exact system, which is the green line here, then we see a reduction in the effective D33. I say this is the effective D33, this is the maximum strain divided by the maximum electric field. So we're seeing much smaller strains as we reduce the field excursion. And then here we're comparing it with the resonance data. And we can see a trend here, and this is something that we would like to develop to measure this in more detail, is to see whether we have a consistent trend relating high field measurements continuously down with resonance type of measurements at a low field limit. But the data at the moment is still a little coarse. One of the things that you may have noticed, because I've put some big arrows on it, is the temperature differences. There are discrepancies in the temperatures of the peaks between these different measurement results. And we're not quite sure why that is. We've looked long and hard at the temperature calibrations in these different systems, and nothing we can find there explains this discrepancy. So it's larger than the uncertainties in the temperature measurement. One factor which could be involved is self-heating, because the materials become conductive at higher temperature. Then when we apply a high electric field, then the sample self-heats, and so really this sample, when it says it's 400, may actually be 400 plus whatever the self-heating effect is. But with the exact system, it applies a series of pulses. They're not very long pulses, and we can't see that would explain all of that temperature difference. It's also mentioned as well as the effect of current compliance. So when we get to the peak in this curve here, then we're starting to see the limit of the current capability of the amplifier. So it starts to drop off the voltage. And so on the high field measurements, that could certainly be a factor. Some of the other things that have an influence on this, things like sample-to-sample variation. I think Tim has shown some results showing that the variation in the room temperature values, certainly they're all quite consistent, but there could be variations in polling from sample to sample on these. These samples have to be repolled, and depending on how exactly that repolling procedure is carried out, then we may get some variations. Okay, so this again shows some measurements, some repeat measurements on the exact system compared to the MPL measurements for D31. And so the black line are the MPL measurements using Pratt, and the two red lines are the exact measurements, resonance measurements, evaluated by the standard. So we've seen this before. We've seen this deviation between the Pratt and the 50324 measurement results. But here we're seeing quite good correlation between the temperatures at which the peaks occur. These have both operated, measurements taken at similar values of electric field, and we're seeing quite reasonable repeatability between different samples. So with similar types of measurements under controlled polling procedures, then we get some consistency in results. Here are some of the measurements. Again, we've seen these results earlier, but I just wanted to show them side by side. And these are on the left we have the MPL interferometer measurements and the exact measurements on the right. These are not directly comparable because we have a difference in the voltage applied. So these are 2000 volts or 1 kV per milliliter, and the exact ones are done at 4000 volts. But if you look at the sizes of the displacement, then they are about proportional to the voltage applied, and we see a larger hysteresis in the higher electric field measurements, which again is what we would expect. So those two sets of measurements look comparable. We see similar trend with temperature. But again, I think this illustrates the point that if we wanted to numerically compare those two sets of data on the same graph, we would have to do them at the same electric field. This is a comparison between the measurements at PTB and the exact system, and you can see that the PTB measurements, this red curve up here, is showing much bigger displacement at 100 degrees C than measurements on the exact system at 80 or 120. So this seemed to be quite an anomaly, and the trend's not going in the right way either. Torsten did some excellent detective work on this to try and understand what was going on. And the reason is that the PTB measurement, we've seen the very large interferometer system. It takes a long time for temperature stabilization. The actual measurement process is not a high frequency measurement. It uses very, very slow electrical cycles, and those time factors had a significant influence on the measured results. So these measurements taken by exact were at 100 degrees C, waiting for 2 hours at that temperature, and then doing a number of measurement cycles before taking the final measurement. And you can see that having done that, we get much, much closer agreement. So the measurement cycle, the measurement time, the time spent at temperature affects these measurement results. And just to show the correspondence when that's been taken into account, so for different measurement cycles, but under comparable conditions, then the blue line is the exact result, the dots are the PCB results, and room temperature, they correspond very nicely, and then at 100 degrees C, then they still correspond very nicely. As Guido said earlier, some of these results at the bottom end were where the sample was failing, so we can't read too much into those. But arranging the measurement cycles, the time of measurement, the time at temperature is all important for getting comparable results. Okay, so I must add as well the stage that we're at in the work is the next 6 months. We will be looking a lot more at doing these measurement comparisons. This is the stage of the work that we're at now. So in conclusion, then temperature differences between the sample and the measurement, the thermometer that you're using to take the measurement needs to be carefully considered and validated. Electric field strength can have a significant effect on both the closed electric displacement but also on the effective transition temperature. Self-heating is a significant issue as samples become more conductive at higher temperatures, and the measurement frequency and the timing of the test can have a big effect as well. Repeatability between samples and repeatability of the polling process. This looks as though if we do those, particularly with the polling process, if we do it in the same way between the different labs, then we get similar results, but if the polling process is done differently, then that can have an effect on the results. And as I said, the next stage of the project is to go into more detail in these inter-comparisons. Okay. Thank you. Any questions?